Hello, my name is Andy Klump, president of ASH WARE, and I am proud to announce ASH WARE's new eTPU graphical state machine tool, which is part of ASH WARE's new DevTool IDE that integrates code editing and simulation. This is the latest tool in a long line of eTPU, TPU, and CPU simulators and compilers. ASH WARE, development tools since 1994. This instructional video shows a port of Freescale's CAM function to a state machine using the ASH WARE graphical state machine coding tool. This tool was inspired by our many customers who typically begin their design by visualizing it as a state machine. Our thought was, why not provide our customers a tool that actually allows them to develop their designs in exactly this state machine format to which they are intuitively drawn. Freescale's set2 CAM and crank functions, architected by Jeff Emerson, are two such examples. Let's look at Freescale application note AN3769, page 24, which shows the CAM state machine. Note that the crank state machine is on the previous page 23. I submit that this application note, which documents the CAM and crank function as state machines, strongly supports this state machine approach. Let's look at S0, S1, and S5. These are invoked by events HS7, LSR, and HS4. One end of all these arrows is unattached, indicating that these can run regardless of the active state when the event occurs. The next three states are S8, S2, and S3. S8 is a transitory state that is entered following S0 or S1, then exited on the first CAM signal edge. S2 is entered and re-entered as CAM edges are detected within the expected engine angle window. If the angle window closes without a CAM edge having occurred, then S3 is entered. From S3, a valid CAM signal causes a return to S2, otherwise a loopback to S2 occurs. This is ASH WARE's Graphical eTPU state machine development tool. Starting from scratch, let's create a brand new state named CAM. Now let's create three new asynchronous thread type states to handle the HSR7, LSR, and HSR4 events. The first state I create is initialization. For state type, I select thread, which indicates that any state change will be handled programmatically. That is to say, the auto-generated code will not change this state. If I had selected state instead, auto-generated code would have automatically changed the state for me. The event that invokes this first thread is HSR7, so I select that option from the thread events. Now I grab the code from the Freescale set2 CAM function. At the bottom of the initialization thread, there is a function called restart. This function will be called in many places and illustrates that state machine coding is built on top of ASH WARE's popular object-oriented embedded C extensions for the eTPU. This restart function must be declared in the auto-generated header file suchly. I'm going to create it here at the top of the C file. One thing that is interesting about this function is the macro force state here. This macro forces the state machine into state seek, which I will create in a bit. Remember that this initialization is an asynchronous thread invoked from HSR7, issued by the host CPU, which is usually used to initialize the channel right out of reset. So, in addition to the other initialization tasks, this initialization thread also sets the state machine to state seek. The second asynchronous thread handles the situation where the crank function has lost sync. The crank channel links to the cam channel to invoke this thread. This thread clears the link event and also calls the restart function, thereby resetting the state machine's state to seek. The third and last thread, which handles an HSR4 event, simply does a coherent write of the cam signal edge window parameters. This thread really illustrates the true intent of a thread in that this thread executes to completion without affecting the state machine's state at all. Okay, now let's create the remaining and most important last four state machine states, which are seek, start angle, sync angle, and sync lost. Let's create the previously mentioned seek state. Keep the state type state so that the auto-generated code handles the state variable. Select the TDL event. Set the TDL event to result in this seek state executing again. This is referred to as a loopback. Let's add the state code. The key here is the global variable eng position sync status G. This is an indication from the crank channel of whether or not the crank has determined the engine's position. Once crank is synced, then cam syncs. Specifically, this jump state macro causes a state change to the state start angle. What is interesting here is that we are again forcing a state change programmatically. It would be nicer to have the state change be done with the state logic. We could accomplish this using the state machine logic by adding a state conditional here. Going back to the state properties dialog, this state conditional appears, and I could use this state variable to help determine the next state on a TDL event. However, we are not going to go this route in this demo, so I am going to remove these and keep this a loopback. Recall that state start angle is arrived programmatically from a macro in state seek. When the first cam edge is detected via a TDLA event, the state machine goes to state sync angle. Let's copy in the code and take a closer look. We happen to be using the match to ordered single blocking transition channel mode. In this mode, TDLA starts out blocked and is opened on a match A event. So if the TDLA cam edge occurs before the opening of the window, which is match A, then it is ignored. However, once a match A occurs, any preceding cam edge will be detected and generate a TDLA event. Match B would normally close the window, but in this start angle state, we want the window open forever, so we clear MRL B but don't schedule any future match, thereby leaving the window open forever. I hope it doesn't snow. Let's copy in the code for sync angle. This state is fairly simple. The set cam edge window function is called to schedule the future window opening and window closing match A and match B events. Now, TDLB is not used in this function, so it is ignored. Similarly, in this particular channel mode, a match A event does not cause a thread, so MRLA is ignored also. The two events that result in threads are MRLB and TDLA, so these are selected and assigned states. Note that there is no next state assignment on both MRLA and TDLB being 0. This is because if there is no event, then there is no state. So this is state execution code. So this is not a valid combination. However, if there is a TDL-A with no MRL, then the cam edge occurred within the window, so I select loop back to state sync angle. In both the other cases, the window closed before the edge occurs. I know that because if the TDLA were to have occurred first, then it would have blocked the MRLB. Therefore, when both TDLA and MRLB are set, the MRLB came first, and there was a loss of sync. The last state is sync lost. Let's add the code. The state properties are about the same as sync angle properties, in which a TDL-A with no MRLB returns back to state sync angle. Otherwise, loop back to state sync lost. Let's build the code. All the C files in this project get rebuilt. I see that there is an error in file cam.c line 38. I click on the error to pop cam.c into view and scroll the offending line. This is a missing #define and a couple of headers that need to be included. Let's include them at the top of the file and rebuild. This time it is successful, but actually slower than it needed to be because not all the files were out of date. Had I selected make instead, all file compilations would have been skipped except cam.c. In this make, I see that nothing gets rebuilt since everything is up to date. Okay, let's take a look at the simulation. I right-click the mouse in the right side of the waveform window. Voila, poetry in motion. This top signal, cam, shows the color-coded state enumeration. The first state, which is colored blue, is the initialization state. As I hover the mouse over the different states, hint text indicates which state is active in that channel at that time. The state in the cam state machine window have also now become color-coded and match the colors in the cam waveform. If I reset the simulation and select Go to State in the pop-up menu, the simulation runs to the start of that state's code. Additionally, the state code pops into view over here. Note that the auto-generated state prologue code has already been executed. It gets created by this cam common prologue code 2 auto-generated tag in the source code. Don't modify this tag because it is used to create the auto-generated prologue. I would note that this prologue has already executed because of its orange color of its code coverage indicator over here. Orange indicates that the code associated with this source line has been partially executed. Fully executed code would be white. I reset the simulator and note that this code coverage indicator changes to black, indicating that the code has not been traversed at all since the reset that I just did. I want to measure the size of the thread that handles sync angle and also see how much of this thread is state code versus how much is auto-generated prologue. First, let's select the cam thread from the waveform options dialog. Note that a cam thread executes on every cam state change. I place the left and right cursors around the red to green state transition from state seek to state start angle. 2 zoom-in cycles are needed because the thread is fairly short. Next, using the down arrow key on my keyboard, I'm going to make the active waveform. The left and right keyboard keys can be used to snap the 2 cursors onto the thread transitions. The delta cursor indicates that the thread time takes 1.1 microseconds to execute, which is very quick. To measure the prologue time, let's make the cam signal active using the up arrow keyboard key and snap to the beginning of the state code. Now, delta cursor indicates that the auto-generated prologue code is 0.35 microseconds. Now, let's say I want to step to the next sync angle state. I find its state code by clicking on the state. In the cam.c code window, this state code scrolls into view. Next, I place a breakpoint by clicking just over the left edge. Then I hit go. The simulation stops at the breakpoint when the state code next begins to execute. I hit step several times and the simulation steps through the code and into function setCamEdgeWindow. That's it for now. Thanks for watching. I could show you a bunch more things, but my boss told me to keep this video under 15 minutes or she would send me down into the mines. If you want a webinar demonstration or have questions, please contact us here at ASH WARE. ASH WARE, embedded tools since 1994.